All right, what we're going to be doing now is we're going to be looking at an introduction to polynomials, which is the new unit. So we're going to be looking at two things. The first thing is we're going to be looking at the behavior of different types of graphs, and then we're going to be looking at long dividing polynomials. So what we mean by a polynomial is essentially a fancy name for just any graph with x to the power of something. So we know when x is to the power of 1, it's linear. When x is to the power of 2, it's a parabola. X to the power of 3, it's a cubic. X to the power of 4 is also a parabola. X to the power of 5 is also like kind of a cubic. They get like really wide at the bottom as well. So they're like a little bit more of a funky parabola and a funky cubic. And what the relationship between that is when we're looking at the roots or x-intercepts of a factorised equation, the power of the root, the power of the intercept determines the behavior that it looks like when we actually end up graphing it. So if the root has a multiplicity of 1, which means it's just essentially like x plus 1 or something like that, the behavior of that is linear, which means it goes straight through it. So if we had something like x plus 1, just going straight through. If the root has a multiplicity of 2, it behaves like a parabola. If x is to the power of 3, it's going to be a cubic. And if it's to the power of 4, it's going to be a parabola-ish. Because it's not going to quite be exactly like a beautiful parabola shape. It's going to have like the wide rear end like that one does. And the reason it has like a wider rear end is only because if we take a quick look from a small table of values of y equals x to the 4, we know that when 1 to the power of anything is just 1. So there's 1, there's -1, and there's 1 there. When we look at these decimals here, 0.5 or 1 over 4 to the power of 4 is a really, really, really small number. That's like 1 in 128, which is going to end up being there. 0.25 or a half to the power of 4 is 1 over 32. So we can see that it goes slow, and then it just shoots up, and it works like that for the negative. So the graph ends up looking a little bit funky. It behaves like a parabola, but not directly. We can use this to help us graph things really, really quickly and really, really easily. Now, the things like turning points and all of that stuff will come when we get further into calculus, but at the moment, we're just looking at the behavior of the intercepts. So let's graph the first one. We have p of x is equal to x minus 1 squared, x minus 2. So we have two different x-intercepts here. Our x-intercepts are 1, and our x-intercepts are 2. Because substituting in those numbers, we get 0. Now, my graph here, it plays like a parabola when x is 1, and it goes through the axes at 2, which means my graph can be one of the two following. It could go like this, it could behave like a parabola at 1, and then go straight through 2, just like this graph in red. It's behaving like a parabola around 1, going up and then down. We're not too interested in that point there. We can find it later, but not at the moment. We don't really need to. We can just make up wherever it's meant to be. Alternatively, it could be the other direction. It could come the other way. It could be coming from below, be a parabola here, and then cut straight through there. So my graph could be one of those two. The best way to determine which one it's going to be is to look at another point. In this situation, the y-intercept is the best point to look at. But if we substitute in any point that isn't an intercept, we can determine if my graph is above or below the line and go from there. Let's find the y-intercept. The y-intercept is when x is equal to 0. We've got -1 squared times -2. 1 times -2 is -2. So it's going to be down there, which means it's going to be the green graph. Whatever, we'll just sack that all off. If you want to see the green graph, go back and take a look at it. 1, 2, going down, behaves like a parabola at 1, goes straight through at 2. Nice, easy way to graph. Let's look at the next one. This polynomial is x cubed, x plus 2 to the 4, x squared plus x plus 1. Now, let's look at the intercepts first. The intercepts are going to be when x is equal to 0 and x is equal to negative 2. The behavior at those points, when x is 0, it's a cubic. When x is negative 2, it's a power of 4, which is parabola-ish. This part here at the end, this part here has no x-intercepts. We can't factorize that. It doesn't work, so it actually doesn't apply, so it's not relevant to our intercepts. It's not going to impact them at all, because when we look at those values really, really close to the intercept, these are going to go to 0, these two things for each intercept, to such an extent that this part don't matter. Don't matter with flawless grammar. So let's begin to see what this is going to look like. Got another graph here. Intercept at 0, that's a cubic. Negative 2, that's a parabola. We once again have two different ways to do this. It could be a cubic, there's a cubic shape there, and it could be a parabola like that, or it could be a parabola like this, and then go through the shape of a cubic down there, knowing that a cubic ends up looking like that, or like that from these pictures that I've just drawn. We need this little weird thing there because we need to make sure we're getting the subsequent shape, whether we're going from cubic to parabola or parabola to cubic. Now, we can't find the y-intercept, and that is because we already know that this graph goes through the origin either way. Best way to look at that is to substitute in any other point and determine if it's going to be positive or negative. So let's put in x is equal to 1. Let's give it a go. So let's sub it in. We've got 1 cubed, which is 1. 1 cubed, 1 plus 2 to the 4, 1 squared plus 1 plus 1. This is all positive. It's just straight positive. So it's going to, the number itself doesn't actually matter. We just care about if it's positive or negative. So because when it's 1, it's going to be positive, my graph is going to end up looking like this one, cubic through there, and then down like there. So there's 0, there's negative 2. It's going to look something like that. Yeah, maybe a little bit more like that, because it's gonna, yeah, it's a rough grab, but that's life in the NBA. There we go. Beautiful. Two different parabolas, and by parabola I mean polynomials, two different polynomials looking at plotting two different things. I'm going to need to get rid of the first one in order to plot the third. So I'm going to quickly just erase what I've done in the first graph, and we're going to look at plotting the final polynomial in this graph here. So, see, Rx, negative 2, x minus 2 squared, x plus 1 to the 5, x minus 1. We've got my three x-intercepts here. We know that x is going to be 2, my x-intercept is going to be negative 1, and it's going to be 1. What these look like at the root or at the intercept, 2 is going to be quadratic, it's going to be parabola. When it's 5, we know that when it goes up in those powers, so like 3, 5, 7, etc., it's going to be cubic-ish. And when it's 1, it's going to be linear, so it's going to be going straight through. So here we've got 1, we've got negative 1, and we've got 2. There they are right there. So like we talked about before, there are two different ways that these graphs can be drawn. The first way would be a parabola here at 2. 1, it's linear, goes through, and then it's a cubic at here, negative 1. The other way would be that, I'll do it in a different color in blue, cubic at negative 1, it's going to be linear at 1, and a parabola at 2. So it's going to be the blue graph or the green graph. Best part about this, we can look straight at the y-intercept. We don't have the y-intercept as one of our x-intercepts, so we can just say the y-intercept will help us determine if it's the blue or the green. The y-intercept is when x is equal to 0. We have -2, -2 squared, 1 to the 5, -1. So we have a negative times a positive times a positive times a negative, which overall gives us a positive, which means it's going to end up being the blue graph. So that right there, that is graphing involving the intercepts and looking at the behavior between them.